Hello everyone. In this session, I'm going to talk about how we can use support vector machines for again classification purposes itself, but in this case, the response variable actually has multiple categories. So in our earlier session, we looked at how we can use support vector machines when the response variable has only two categories, which is a binary classification. But here we are talking about the response variable having more than two categories. That is why we are calling it as multi-category data. Now, in this regard, we would be talking about five different algorithms. The first one being the CSVM, which is the classification support vector machine. Then Nu-SVM, Nu being a parameter. Then we have three more mechanisms. One talking about bound constraint CSVM classification, Western Watkins multiclass support vector machines, as well as Kramer-Singer multiclass support vector machines. Now, just like the way I have been dealing with other sessions as well, this is not a math oriented session, right? These are different algorithms that are designed by different sets of people. All of them work with the concept of support vector machines itself, and they are all packaged into R as a part of different packages. So I am a user of all these techniques for my data. Here my data is here my data should contain a response variable which is more and more categorical, and more importantly more than two categories. So I want to use that one single data set for trying to create a support vector machine based model with respect to all these five different algorithms. And based on that, I really want to assess for this particular data set which I have considered, which model will be more and more appropriate. And depending on the way I assess the appropriateness of the model, I would be using that corresponding model for the prediction purposes as well. So that's the business usage of it without really getting into the mathematics of each of the objectives. So here, straightforward, I have a data. So I want to understand within this data, I have to figure out what is my response variable and what are all my attributes. So these attributes are the kind of drivers for the values associated with the response variable. And here the response variable is definitely categorical, and that too with more than two categories. Whereas here the attributes, or sometimes people call them as covariates, they may be either categorical or numerical in nature, whatever it is. So wherever I have such a kind of a business situation and I want to try to link the response variable with a set of attributes using the support vector machines mechanism, I can use one of these five algorithms. Probably I should use all five of them, see which one is more appropriate for this particular data. We'll talk about how we assess which one is more appropriate, but as there is no mechanism which clearly says theoretically that model 1 is always better than model 2 or some such kind of a relation, I cannot discount any model in the beginning itself. I may have to try all the algorithms, fit all possible models, evaluate which set of models are more appropriate for this data, and based on that evaluation and assessment, I may have to decide using a particular algorithm or using a particular model for futuristic prediction purposes. Right? Here, the data set that I would be considering is the data set with respect to the hospitals. So let me just load that data set. We'll have a quick discussion on that data set. So it's there in my folder. So I'm loading it into a variable called hosp as a part of R loading. So within this hosp, if you just see dim of hosp, okay, so it has 4406 rows and 13 columns. That's the size of the data, right? I can very well look at the structure of hosp just to understand what are the data types. So here we have health status, which is a factor with 3 levels: average, excellent, and poor. So this is a factor variable which I would be taking as the response variable. The health status, in this example, I'll be considering the health status as the response variable. And because it's a factor, I can very well go ahead using the multi-category classification algorithms. All these 5 algorithms I can use. With this as my response variable, I want to really assess whether the health of the person is good or average or poor based on a few attributes. How many times he has visited the doctor, right? And based on how many emergency visits he has typically made. How many times there was a stay in the hospital? How many chronic conditions this person is having? What is the age of the person, gender of the person, the marital status of the person, number of years of education of that person, family income of that person, whether that person is currently employed or not, whether the person has a private insurance separately or not, and whether the person had a Medicaid feature or not. Medicaid feature did he subscribe to or not. Now, going with all these things, I really want to assess what is the typical health status of the person. So I will be taking this as my response variable, and probably I can look at all of them as the attributes which are used to determine this particular response variable. So let's get started on that data with the model number 1, CSVM. And CSVM is actually an implementation that is found in the package E1071, and the function is SVM. So probably I can very well load the E1071 package. If it is not installed, you better install it. But I think it's already installed on my system, so I'm simply loading that E1071 package. And once I have loaded it, I will be using this SVM as the name of the function. So let me just see what this SVM function is doing for me. SVM is a support vector machine. SVM is used to train a support vector machine. It can be used to carry out both general regression as well as classification. Right, I can use it for both regression as well as classification. Regression is more of an epsilon type, and classification is of a nu type because we have different parameters associated with each one of them, and a formula interface is provided. So as an input here, I am always looking at SVM, the X variables, right? Or I can look at the formula base. Here I will look at the formula, where I have a formula which is a dependent variable or response variable tilde the attributes that are used to work with the response variable. Then data, I can very well provide the data, and I should also give a few other inputs, especially with respect to what is the kernel function. Now in this case, if you look at the kernels, there are different kinds of kernels that it is supporting. It will support the linear kernel, polynomial kernel, radial basis kernel, or sigmoid kernel. When I look at the examples at the bottom, you could see that in the kernels, in the kernels here they did not specify any kernel. Okay, so parameter needed. So if it is a polynomial kernel, I have to specify the degree. If it is for all the kernels except the linear, I need to specify the gamma, where the default is 1 by the number of columns in the data, and coefficient 0 also I need to, it's a parameter needed for the kernels of the type polynomial and sigmoid. For that I have to specify the coefficient 0 as well. So for different kinds of kernels, different computations are very much required. So I can, by default the kernel is a radial kernel, but I can very well change it to a polynomial or any of those kind of kernels as such. So you can change, right? The radial kernel, you can change it to linear, polynomial or sigmoid kind of kernels. But depending on the kernel type, we have to give the variables, we have to give the parameters also appropriately. By default, the cost is set to 1, right? The gamma is set to 1 by number of columns. So the degree is set to 3. So these are the default settings. But depending on the kind of kernel that you are using, the parameter values may keep changing accordingly. Now let's get back to our data to work on it. So the kernel is the kernel function, one of the 4 functions I can provide. The cost is the cost parameter, which talks about the misclassification rate in the process, and I have a multi-category response variable y along with the data of the various covariates. So in the process, initially I have to load the E1071 package, already done. Get the necessary data with a multiple category response variable. So let me just check for if there are any kind of NAs or some such kind of things in the data. There are 3,500 people who have an average health status. 343 of them are having excellent and 554 of them are having poor. And I don't see any kind of NAs as a part of any of this data, so I can very well be comfortable with that. So do a preliminary inspection of the data in terms of assessing the summary of the data. Also check if there are any NAs. If there are NAs, come out with ways in terms of how to handle these NAs. Then split the data into a training set and a testing set, right? So we already know how many records are there, but let me quickly check it. N row is talking about 4,406 records. So it's better that I take the 70% of it to build the model. So almost 3084 would be used to build the model, and the remaining of them will be used for the testing purpose. So let me set the seed so that the same set of data can very well be used for all the models. So randomly I am selecting out of the 4,406 values. Randomly I want to select some 3084 values and assign them to the variable train. So that's where I am saying sample 1 to 4406. So out of the chits number 1 to 4406, randomly pick up some 3084 of them where there is no duplication at all, which means replace is set to false. So with this we have 3084 records that are pulled. So now I can create a train data from this train, wherein I am taking the subset of the host. I'll take a subset of host where the rows are train number of rows and all columns. So that will become my train data, and I can have my test data typically is those subset, that particular subset of the hospital which does not contain the train, which means all omit the rows that are contained as a part of the train and take all the other rows. So this is what is the split to the training data and the testing data. So we have done this aspect now. Split the sample data into a training set and a testing set on a random basis. Then comes estimating the support vector machine using the default settings of kernel and cost. As I have discussed earlier, if you look at SVM, right here, the default settings are kernel. If I am going with the radial kernel, I require the gamma. If I am going with polykernel, I require the degree equal to 3. So the default ones, degree will be 3, gamma will be 1 by number of columns of x. So here I have 12 different columns for x because my whole data is 13 columns. So my attributes are typically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 columns. So 1 by 12 would be the default value of gamma in case of radial. Similarly, coefficient of 0, coef 0 will be taken as 0 for both gamma as well as polynomial. And even in case of the cost, the default would be set to 1. But other than that, we may have to try the different values of cost and the parameter values. So initially, I can fit the SVM by just taking the default settings as it is. So I'll call it as fit default, right? Fit default, and let me call this as radial. We'll try other kernels as well. So we are going with SVM. My dependent variable is health underscore status. That is what is the response variable for me, and all others are used to determine this response variable. So that's where I'm putting a dot. The data that I'm using in this case is the train data. So this is what is the basic model that I'm building. Default radial. Okay, so the fit default radial model is done. Similarly, I would also do the fit default poly, right? If I have to go with the fit default poly, I have to clearly specify the method, right? So let me just look at what is that I have to specify as a part of the method. Polynomial is the type, no, not the type, kernel. The kernel, I have to set it as polynomial. Okay, so let me go ahead with it. Fit default poly, and I would be setting kernel equal to polynomial. So this is the polynomial kernel that I have fitted. Then I can also fit the linear kernel. So we have fitted the polynomial kernel out here. I could also fit the linear kernel, right? And I can also think of fitting a sigmoid. If you look at the kernel, I can also fit a sigmoid kernel. So let me try all 4 of them, and we'll also talk about how do I change. So the default all 4 kernels I have used. I'm using the sigmoid kernel as well. So these are the 4 different types of models that we have fitted by default. Okay, let's see what each of these models are giving us. Fit default radial is saying the formula health status tilde this, data is this. It's a C classification, which is the type of SVM that we are going with. The kernel is a radial kernel. The cost is 1 and gamma is 0.076 because it is 1 by the number of columns. So we have 13 columns. So 1 by 13 is 0.076. So that's the value of gamma. And you could see that there are 1594 support vectors that are typically created. So that is what is the typical output that has been given out of this, and probably a little bit of more details can be obtained using the summary. A little bit of more details. So the three classes that we are talking of here, right, the three classes that we are talking of, 957 into the first class, which is the average, 380 into the second class, excellent, and 257 into the third class, which is poor. So that is how the fit default radial has typically created. Now the same logic I can try out with the other set, right? I'll go with summary of fit default poly. If I go with fit default poly, you could see the default cost is still 1, the degree is 3, right? By default the degree is taken as 3 and the gamma is taken as 1 by number of columns. But here the classification is with this 1388 support vectors. The classification is coming out like this: 764 of them are coming into average, 367 into excellent, and 257 into poor. This is the classification that is coming out for fit default poly. And what about the linear kernel? Linear kernel has resulted in slightly different. The cost is 1. Here I don't have the value of the degree D, right? So here I could see that this is the classification that came out: 718, 382 and 257. So probably in case of poor, it looking the same in both the groups, but slight difference between the excellent and the average. And even the support vectors here are 1388, whereas here it's only 1357. And similarly, when I am getting into the sigmoid, the scenario is slightly more different, right? Here you could see the number of support vectors are 1096 with a classification of 530, 317 and 249. So that's the default. I'm examining the summary of the fitted models in each of these cases, the details of the type of the support machine, right, the kernel that we have used in each of the cases, the cost parameter, the gamma model, all these values are typically obtained. But now I can very well play around in terms of the values associated with each one of them, right? I can tune, I can change the parameters, and based on the parameters I could see which combination of the parameters is going to give a very good estimate for the parameters, right? I want to change the different values of the parameters and see which one is doing the classification more and more appropriately. Now this is where we can use the tune.svm as a function, right? Probably if you see here tune.svm, it's a very important function, convenience tuning wrapper functions. So I can use tune.svm. So here I can very well specify the x and y values for the tuning part. I can use this tuning for almost every mechanism which you could see here. I can specify the data, the gamma values I can very well specify from which range to which range I want the set of gammas to be tested. Even the cost function I can very well specify from what value to what value needs to be tested, and based on that I can very well look at the one that is resulting in the least possible, which means it's the best possible model that has actually emerged out. So that is what I can go with the tune.svm. So what I want to do is I'll go with object. I'll create an object using this tune.svm function, right? I can provide the formula directly. The formula is health state as tilde dot. That's the typical formula that I am providing, right? That's the first input that I have to give. Then data I can very well give. The data for me is my train data, right? Then I could also specify, if it is a radial, it's better that I specify the gamma values. So gamma values, I can very well take them as a sequence. I'll take all possible values of gamma from 0.01, right? Probably I can very well take it like 0.01 to, let's say, 10, or whatever, 0.01 to 10, with a pi equal to 0.01. So we have so many different possible values of gamma coming up. And similarly, I can also take the cost, again ranging in a different range altogether. The cost also, I can make it lie in a completely a big range of costs, right? So that I can very well evaluate the misclassifications. So wherein I can look at 1, 2, so I can very well say cost is anywhere between 1 to 32, or probably the number of misclassifications, right? So probably let me make it 1 to 100. So that's the cost parameter that I'm trying to bring out for this data. So I'm trying to experiment with all possible values of gamma and with all possible values of cost, which I'm going with. The method is radial itself. So let me see how it gets executed. Because of so many combinations, it might very well be possible that it can take some amount of time. The processing speed, the processing time are more and more important in this context, because we are experimenting with different values of gamma and different values of cost, based on which I can look at the best performance, which is more to do with the misclassification rate. So like this, we can very well plan even the other methods as well, right? I can plan it out with the polynomial, I can plan it out with the linear or different kinds of kernels. I can very well plan. So based on this, I should get what is the best value of cost and what is the best value of gamma, which we can very well use. Depending on the best value of the cost and the best value of gamma, we can again refit the model, and based on that refitment of the model, we can very well assess the accuracy of the model. So let it first give me the values of gamma. Based on that, we'll see if there is any improvisation in terms of accuracy. We'll try to fit both the earlier model, the radial, without doing this tuning, and the model where the tuning has been performed. So let's see, it may take some time for execution, but once we get our values, we can see if there is any kind of an improvisation to the value of gamma. By default, it has taken as 1 by the number, and cost has been taken as 1. Normally it's taking too much of time, because we have almost 1,000 different values of gamma to be tested, and probably 100 different values of cost to be tested. It looks quite a heavy stuff. So let me see if I can cut the model out here. For your understanding purpose, let me change the gammas from 0.01 to 1, incrementing it by 0.05, and cos, instead of taking it from 1 to 100, let me take it from, again let me take it as a sequence from 1 to 50 by 5. So the overall number of values are typically reduced. So let me just see if there is any kind of an improvement in the overall fine tuning process. Even this is taking quite a good amount of time. So what I suggest is, let's knock it down to very few values because we just need to check it out. So let me set this from zero point 0.01 to 1 by an increment of, let's say, zero point 0.2 for gamma, and even the cos parameter, let me set it from 1 to 50 by an increment of 10. So let's see if this can execute slightly faster, right? Or probably even let's reduce it even more further, 0.25. I just want to make sure that you understand what is happening as a part of the tuning process. So it's as good as we are trying out different possible values of the train data, different possible values for the parameters gamma as well as the cost function, running the model those many times. Right, that is what is more like the tuning part. It's as good as trying out different possible values of gamma, different possible values of cos into your SVM function rather than taking the default set of values. We want to see which set of values for gamma and cos will give us a most optimal kind of result. Now we could see that the whole tuning process is done. So once the tuning process is done, I can very well look at the summary of this tuning process to see what gamma is more and more appropriate for our case. And now you could very well see the error in each of these cases. The best performance is having 20% error, right? The best performance is having an error rate of 20%, and it's saying go with a gamma of 0.01 and a cost parameter of 41. That is the place where we are getting the least possible error, right? 0.01 and probably 41, having an error rate much lesser, and the dispersion also looking like slightly on the lower side. And if we really go ahead in terms of fitting the model with these, probably it's like a improved fit, not the default radial, I'll call new radial, right? I'm doing a fit new radial where I'm using the SVM function, right? The input is health status tilde dot, which is my formula, and I have my data as train data, and I also have my cost parameter. Now I am setting it to 41. I should have tried many more combinations. Similarly, my gamma parameter is coming out to 0.01 in this case, and using these I'm going to go with a fitting of the new model. So I'm calling that as fit new radial. So even this I'm taking a summary of this fit new radial. Now I want to compare all these models that I have in front of me. So the number of support vectors is 1541, 907 into the average, 377 into excellent, and 257 into the poor category. So that is how I am getting my values, my classifications across. Right, and if I actually put the cross validation, right, the same model, probably if I am putting the cross equal to 10, where the cross validation also will be performed, and in each of the cases I would also get the accuracy of my model in all the steps. So let me set cross equal to 10 so that I can look at the accuracy in each of the steps along with all these things that are being supplied to me. So with a cross validation of 10, I'll get even the total accuracy and accuracies in each of the 10 different runs that have been performed. So now let me see, once I put a cross validation of 10, it is like it is executing 10 different times, and basically from there I could see what are the accuracies. Overall the accuracy is around 80%. Right, even individually if I'm looking at 76, 84, 77, so the minimum looks like 76 and maximum looks like 84 in the process. Right, so with this, that is the level of accuracies, which means the errors are to the extent of 16 to 24%. But overall, now I can get into the prediction part on the testing data. Right, now predicted. First, let me go with new radial. I can also use my fit original ones. So I'll say predict fit new radial. Right, I'm using the predict fit new radial and I'm doing it on the test data. Predict fit new radial. Error in predict. Fit new radial is not, oh, radial I have actually called it RE looks like. Okay, fit new radial. So the same way I can continue all my earlier models. Fit default radial. Fit default radial. So I'm calling it as predict default radial. Okay, then I can also have predict default linear. Right, I can check all the models. Even fit default linear is my model. Similarly, I can go with poly, fit default poly, and I can use the predict default poly, and I am also using sigmoid. Here the model is fit default sigmoid. So you can create any such number of models, right, wherein you can very well assess which model is more and more appropriate by doing that fine tuning part. But now that these are the 5 models that are available in front of me, I can very well look at the tables for each of these 5. So pred new radial is the predicted values, and the actual values I can get from my test data dollar health underscore status. So I'll get it as test data dollar health underscore status. So this is the table for the actual versus the predicted, which means the accuracy rate when I'm going with the new radial model, everything is coming out to be average itself as a part of the prediction. I could see that everything is coming out to be the average itself, whereas in reality we have 1062 average, 86 excellent, and 165 poor. So the accuracy is coming out to be 1062 plus 7, 1069 divided by 1069 plus 88 plus 165. Right, I can very well find out the overall total, which is 1064 plus 86 plus 172. So overall is 1322, and accuracy wise it is 1069 divided by 1322. So it's almost 80.86% accurate when I'm going with the predicted new radial. Whereas let's try out the other models. If I have to go with the default radial, at least to see whether default is better or worse compared to this, if I am going with this table, it looks like 1068 is correct. So hardly there is any big difference when I am going with radial. 1068 out of this, so 80.78 is the accuracy in this case. But if I am trying out the other models, wherein I am focusing on instead of radial, let's say I'm going with linear. The accuracy is 1064 out of 1322, resulting in 80.48. Now when I'm going with polynomial kernel here, probably the assessments are not coming out that better. The polynomial kernel is still coming out as 1057 plus 9, 1066 out of 1322. Even the polynomial kernel did not work better in this case. And finally, even if I am trying out the sigmoid for this case, I don't think we got anything better. Yeah, sigmoid looks like at least a different result altogether. Probably we should try out different parameter values with respect to the sigmoid. But yes, 43 plus 953 plus 937, so only 990 out of 1322. But you could see that the spread is much better, 74.88. So I should have tried within the sigmoid, I should try different parameter values associated with the sigmoid. I can play around with the parameter values associated with the sigmoid to really see if I can very well improvise on this classification for much better result. So this is how I can very well use this support vector machines for identifying the multi-category classification of the data. Right? So let's look at it. We have tuned the model. From now onwards, I am not going to look at the tuning process, because one, it will take too much of a time. When you are working in the real world, yes, you better get your process tuned so that the parameter values, you are going to get the optimal values of the parameters by doing the tuning. Tuning is very much applicable wherever you are using the 1071 package. You could have used it for neural networks, you could use it for decision trees, you could use it for support vector machines. In various applications you could use the E1071, and wherever you are using E1071, there is a process of tuning to find out the optimal set of parameters. right? We can very well play around with the different parameter values, and based on that get the optimal ranges for the parameter values for different kinds of kernel functions. So you can keep doing this process again and again. Finally, do the prediction with the model and the test data. Look at the confusion matrix, and based on that, narrow down on what is the error rate and what is the accuracy associated with the model. So that's the typical process you need to follow for multi-category classification. Now, on the same lines, just like the way we have used the CSVM algorithm, now we can use the Nu-SVM algorithm. Even that is used using the E1071 package itself. The only difference being in the kernels, again you can play around with all the kernels. Now again I would try to showcase only the defaults now, right? We'll use four default kernels: the linear kernel, the polynomial kernel, the sigmoid kernel, and as well as the radial kernel. We are using these four types of kernels. The type is set as new classification in each of these four categories. In each of these four different types of kernels, but the type will be set to new classification itself. In that case, it goes with Nu-SVM. And if you see here, the new value by default, the default value of the new is typically set to 0.5, which means again you have a scope to play around with the values of new so that you can get the best possible output. Now going with just executing the same on the data, I've loaded this package. All these things are exactly the same. Now estimate the support vector machine using the default stuff. So I will use the parameter values by default. So and we will build the four default. So we'll say fit default linear new. Fit default linear new, where I am using SVM. My reference variable, response variable for me is health status tilde dot. That's my formula. The data for me is the train data. Then we also have the type as new classification. So I am setting it as new hyphen. You could see in the help out here, the type I can set it as, earlier it was a C classification type. Now I'll set it as a new classification type. New classification, the default is C classification, but now I'm setting it as a new classification. Kernel for me is the linear kernel, and all other things are the default ones. So this is what is a fit default new kernel. What had happened? Specified new is infeasible. For this data, looks like the by default the new value is infeasible. Okay, so I'm setting a different value of new because the specified value of new is looking like infeasible for this. So I have specified, so instead of taking a new parameter value of, let me see if I set it to 0.5, is it working? No, for 0.5, which is a default, it is not working. So that's where let me set it to 0.05 and go ahead with all other models. So instead of linear, I could also look at fit default poly, fit default poly new. So here the kernel type, I'm setting it as polynomial kernel. Similarly, I am going ahead with the radial. So I'll call it as radial new, and even the kernel, let me set it at radial. Again, here there is no one single way to directly make out that this is the kernel more suited for this kind of a data. It's better that I play around with all the possibilities, and based on that I can test it on the test data to really make out which is more and more appropriate for me. I can try the sigmoid as well. So 4 different defaults. Why only default? Now I can actually change the parameters. I can tune the parameters. So many combinations can very well be generated. But for the moment, I'm looking at only the 4 types of defaults. Right? I could have simply done the tuning as such, ranging from different values of new. The new values could be anywhere right from the beginning, 0.01 to let's say 0.5. Here we have taken it as 0.05, but I could have taken all the other possible combinations of new to typically evaluate the process. So that's a simple looping that we are expected to do. But if I go with details of each of the models, let me take a summary of each of these models to start with. So in this case, the new is 0.05. This is the gamma. We have 323 support vectors, and this is the classification. Whereas when I am looking at fit default poly, this is the classification. 1388 support vectors have come out with this kind of, oh sorry, I require new coming up in each of the cases. Summary fit default linear new. Similarly, poly new. Poly new is giving me that there are 1402 support vectors with this kind of a split. And when I am going with radial, so this is what is the summary: 1652 support vectors with this kind of a split between average, excellent, and poor. And finally, when I am going with a sigmoid, this is how my summary has come out. Only 302 support vectors with 143, 80, and 79 as the typical classification. Now I can very well go ahead with different parameters of gamma as well as nu depending on the model that I am going with. But whatever is the case, now assuming that these are the 4 different models that I have with me for the fitting purpose, I can very well use these 4 models for the evaluation. So I will say predict new linear. Predict new linear, where I am using the predict function. The model I am using is fit default linear new. That's the model. Fit default linear new. That's the model that I am using. And the data that I am using is the test data. So this is the predict new linear. Similarly, I can go with poly just to see which one is working out more comfortable in each of these cases. I'll go with pred new poly, and similarly I can try out the radial default radial new. Pred new radial is another thing that I can use. And finally, I can also do the prediction with respect to the sigmoid model that we have created. Right, I am using even for the sigmoid. So these four models we have created. Now better get into the tabulation of all these four. So this is the predicted values for me, and the actual is coming from test data dollar health underscore status. Test data dollar health underscore status is what is the table. With respect to the linear, wow, this is looking slightly better with the total numbers. What is the total number of observations? 1322. The test data is 1322. Wow, the accuracy is coming out pretty pathetic when we are going with new, and that too new classification, that too with the default. Probably I could have changed the different values of new to get a slightly different objective altogether. But here the accuracy is coming out in the linear model 532 plus 42. 574 out of 1322 is the kind of accuracy which is around 43% going with a linear new classification, right? But when I try it with poly, let me see if there is some kind of an improvement. If I am going with spread new poly on the test data, this is coming out to 542 plus 59, 601 plus 36, 637 out of 1322, resulting in 48.18% error. When you are going with a polynomial kernel function, then these are all defaults, let me tell you. Probably I could have played around with the parameters and I could very well change the estimate. But just showing, just by changing the kernel function, how the results are going to change. Now if I had used radial, you see the results are completely different, right? 824 plus 18, 842 plus 48, 890 is the accuracy out of 1322, resulting in a 67.3. So in this example, having a radial kernel is much more appropriate rather than using a linear or a poly kernel. Probably now using the radial kernel, I would like to change the estimates of gamma and the new parameters so that I can very well improvise the overall predictability of the model. Similarly, if I try sigmoid, is there any kind of an improvement? Sigmoid is looking pretty pathetic. 181 plus 6, 187, and it's only 257 is the accuracy rate here out of 1322, resulting in hardly 20% accurate. So I would not like to use the sigmoid function at all, but probably I would like to try the radial itself, changing the values of the gamma and the nu. So that is how I can, that's the kind of a flexibility I have in terms of improvising the model and get into the process of estimation and creating a model which can be used for predicting the class to which a particular data belongs to, especially in the case of multi-category kind of a data. So this is what probably you can quickly look at the whole process. Here also I could have used the tune.svm to get the best model for gamma and nu. Right now we have used the defaults, right? Especially when I am using the radial model, I have got the default has given me 67% accuracy. Now I can see by changing the gamma and the new values, can I improve the accuracy level from 67%, let's say, to 70, 80 kind of a percent. So I could have tuned the model to get new values of gamma and nu, which can really help me in terms of improvising the model. And even there is an automatic tenfold cross validation that would be performed, as we have seen in the earlier case. There is a misclassification rate also that is specified. And once the model is tuned, if required, I can very well do the visualization of it, so that wherever the darker the shading is, I can think of the better fitment of the model. So probably in the earlier case, I have actually done that fine tuning. So that tuning, if I am doing a plot, you could see the darker region. Wherever the region is very dark, this is the whole light region. But here it looks like a very dark region. So that wherever the region is more and more darker, I could see that that should be my chosen value of the parameters. So that's how I can very well look at choosing the values of my parameters, and based on that I can get into the retuning of the model with the new values of gamma and with the new values of nu, and again going ahead with the summary of all of them. So this process can keep on continuing as long as I am able to increase the accuracy of the model on the testing data, along with reducing the error rate or misclassification rate with respect to the testing data, right? So after that, after everything, after every model that is being fitted, I can very well use the predict method to test the data on the test data, to test the model on the test data. Based on that, look at the cross confusion matrix classification results by creating a confusion matrix. On the diagonal is the accuracy. Anything that is lying away from the diagonal is the error rate. Compute the error rate of the model, and whichever is the one that is giving me the least possible error rate on the testing data would be the model that I'm going to choose for the final prediction purposes as well, right? That would be the typical process in case of multi-category classification data. So now, till now, we have looked at two important algorithms in that regard. One is the CSVM algorithm, the other one is the Nu-SVM. Again, the process still remains the same in all of them, except that the type is set to C-SV classification. In case of the first type, you set it as Nu-SVM in the second type. Now we would move on to the other types, which are the bound constraint CSVM classification. We'll try to apply it for the same data, say, and see if there is any kind of improvisation in the overall prediction process, right? Now, looking at the bound constraint CSVM classification, even this is targeted towards multi-category response itself. But this is accomplished not through the E1071 package, as we have executed the CSVM as well as the Nu-SVM. These two were executed from the E1071 package, whereas the bounded constraint CSVM is executed from the Kernlab package. So which means I have to install this particular package Kernlab, right? I'm installing this particular package, install.packages Kernlab. I have to install this particular package. Alright, the Kernlab package is installed, and I am very much loading the same package Kernlab. Loading this package Kernlab, fair enough. Now, here we would be using this function called KSVM, wherein the most common parameters that I would be specifying are y, which is my response variable. The response variable again is a multi-category response variable. So the number of categories in it should be greater than or equal to 2. And the covariates in this case I'm taking the dot, which means almost all the variables would be considered as a part of covariates. I have to specify the data which would be used for building the model. I have to specify the kernel function. We'll see what all kernels are supported by this KSVM function. In our SVM function of AE1071, we had 4 kernels being supported, one being a linear kernel, then we had a polynomial kernel, then we had a sigmoid kernel function, then we also had a radial kernel function. So these were the 4 that were supported as a part of the SVM function. We'll see what are the kernels that are supported by this KSVM function. So I can create those many models. Then the type has to be CBSVC, support vector classification. Right, CBSVC is the type that I have to set. One is the bound constraint, B is standing for the bound constraint, C type classification, and the different kinds of parameters that I have to give. Depending on the kernel, we have different parameters. If it is the radial kernel, I require the gamma value to be given. It also requires the cost parameter to be provided. Then similarly, the nu has to be provided wherever required. If it is a polynomial kernel, the degree has to be provided, the d value. So those specific parameters need to be provided depending on the kind of kernel that we are using. So these are some of the important things that we have to give to the function. So let me see what this KSVM as a function is giving to us. KSVM is there as a part of the Kernlab package. Support vector machines are an excellent tool for classification, novelty detection and regression. We have been using for classification and novelty detection till now. They support the well-known CSVC and Nu-SVC for classification, one class SVC for novelty. We have already tested it out. EPS, SVR, support vector regression. Nu-SVR, again a support vector regression for the regression related stuff. Now, the way we are specifying the formula, if we see here, there could be a formula based way of going ahead with this. So we have specified a formula, right? Data equal to null and a set of parameters. Now in the parameters you could see, you could use the kernel, right? In KSVM we could see that the default is scaled equal to true, which means the scaling is already done. Type, let's see what is this type. Type is any one of these. Right here we have typed it as, we are saying CBSVC. CBSVC is bound constraint SVM classification. If I put it as CSVC, I could do a C classification, which I have done already from E1071 package. But I could have done even from here as well. Similarly, Nu-SVC, if I had used, I could have done a new classification. This also we have done from E1071 package. So now we are looking at CBSVC, which is a bound constraint SVM classification. We are also going to look at these two also in the next in this session itself as the next two algorithms. We are going to look at SPOC SVC, which is the Kramer-Singer native multiclass, and KBB SVC, which is a measure of Western-Watkins native multiclass. We are going to look at these two algorithms as well using the same package, so that will simplify our process altogether. In simple sense, I can use this single package to execute all the 5 different classification models in one single shot by changing the type of the method. So that's one advantage with the type. Then kernel, RBF dot. You look at the kernels that it is supporting. RBF dot is a radial basis kernel, which is a Gaussian kernel. Poly dot is a polynomial kernel. vanilla dot is a linear kernel, tan h dot is a hyperbolic tangent kernel. You see there are so many kernels that are supported here. Laplace dot is a Laplacian kernel. Bessel dot is a Bessel kernel. Again, each one of them have their own formulas, their own transformation mechanisms when we talk about them mathematically. But when we are the applied users, we can very well try out all these combinations: ANOVA RBF kernel, spline kernel, and string kernel. So we are very much we can very well specify any of these kernels for our model. Now the k parameters, which talk about the list of kernel parameters that you have to provide. Sigma, you have to sigma inverse kernel width for radial basis kernel. So if you are going with RBF dot or probably Laplace dot, you should be able to give the sigma inverse kind of a kernel. Degree, scale, offset, these three parameters you have to give for polynomial kernel. Scale and offset you have to give for hyperbolic tangent kernel. Sigma, order, degree you have to give for Bessel dot kernel. Sigma and degree you have to give for ANOVA dot kernel. And again, some of them you have to give for so these are some of the different kinds of parameters you have to give depending on the kind of kernel that you are choosing. The cost constraint you can also play around with. The default value is set to 1. Right, this is more for regularization term in the Lagrangian formulation. The new parameter is very much required for all these the new related SVM, SVC and one SVC. So it's a kind of an upper bound on the training error and the lower bound on the fraction of the data points to become the support vectors. So that's a kind of an upper bound that we are typically setting. In case of regression related, we are also giving an intense insensitive loss function, which is the epsilon. We have to give, there is a default value of 0.1 that is being set for the epsilon value. So these are some of the things that we are going to specify as a part of the model, right? And you could see there are so many default things, right? The k parameters, if you see, by default there are a set of parameters that are chosen for all the automatic parameters. So sometimes if I don't give any, just giving the name of the kernel will suffice because the parameters will be taken automatically. The default set of parameters will be very well taken. So let me go ahead implementing the same. We have loaded the Kernlab package. We got the necessary data. The basic inspection on the data is already done. We have even split the data into a training data versus a testing data. Now we are going ahead in terms of bound constraint support vector machine using different kinds of kernels. So initially we can very well go with the default set itself, but after that we can start improvising the set of values. So let's start going with each of the kernels, right? So probably let me call as fit linear kernel. So I'm using KSVM method, wherein my dependent variable or the response variable is health underscore status tilde dot. That's the formula. The data for me is coming from the train data. The type, I have to in this case set it explicitly as C hyphen BSVC, which is the bounded support vector classification. So I am setting it as C hyphen BSVC. Then kernel, I am setting it as vanilla dot. So let me set the kernel as vanilla dot, and k parameters I can very well set them to be automatic, right? I have something. Even if I ignore, it will take it as k parameters are taken as automatic, but I can very well change the parameters. So I can very well say k parameters, and probably I can start giving the list of all the parameters that are necessary for that particular model. We know that for each of the kernel different set of parameters are required, and we have to give those kind of parameters. And we can also do a cross validation with 10, right? We can get a cross validation parameter also, so that for different combination it will try to compute the overall fitment, and based on that it will give us the results of the fitment to the linear. Okay, k parameters should be a list. So if I omit it, I think it will typically take all the necessary parameters. So I can very well omit it and see no, kernel equal to vanilla dot CBSVC kernel. I have called it as vanilla dot. Let me see if I have to give in quotes. Kernel is vanilla dot. Yeah, the vanilla dot I am giving it, and by default the kernel parameters are very much coming out here. But I have an option where I can change the kernel parameters also. These are the automatic setting of the kernel parameters. So I can very well go ahead in terms of looking at print fit linear, right? Or I can look at the summary of fit linear. So I could see that it is CSBC. The default cost parameter is 1. I can play around with it. The number of support vectors are 1307. The objective values are something like this: minus 515, minus 765. So the training error is very important. The training error is coming out to 22.95% here, going with this. So let's start the vanilla dot, right? Let me just see here. The vanilla dot has given a training error of 22.95% and a cross validation error, which is much more reliable, giving it as 23.18%. So probably this is more reliable compared to a training error, because in cross validation 10 different combinations are very much looked at for the fitment of the final model. Again here let me tell you, the parameters I can again play around. Remember that I am using only the default parameters right now, right? So probably let me now change this from fit linear. So let me call it fit poly, and here the kernel I will change it to polydot, right? That is the name of the kernel, polydot. So I'll change it to polydot, and let me try the execution of this particular model. So again the default parameters have come up, right? If I look at the summary of this fit poly, okay, it's only giving only this much. So probably that is where I think I can type in the fit poly or probably the print fit poly, either of them. If I am saying fit poly, if I am going with a polynomial fitment, you could see the default parameters are degree is set to 1. I can play around with different degrees. Scale is set to 1, right? I have to play around with again different kinds of scales, and offset is also set to 1. And based on this, the number of support vectors that are being created is 1270. The training error is 20.71%. So probably this is looking like, compared to a linear kernel, training error is 20.71 and cross validation is 20.72. So you don't find too much of a change between the training and the cross validation errors, especially when we are looking at polynomial kernel, right? Again the CBSVC itself. Similarly, when I now move on to a radial basis kernel, Again, I can change the name of the kernel. I'll call it as RBF dot. Now, in this mechanism, the kernel fitment is happening slightly, it's taking slightly more amount of time. That is what we could see out here. Okay, so now when we are trying to type out the fit radial, which is using the RBF dot, even in this case, the training error is slightly lesser. Again, the default parameters are what are being looked at. The sigma value is 0.138. I can very well play around with the different values of sigma and see if there is any improvisation in the model. Training error is only 18.57% through this, slightly better compared to all the models. But when we are doing a cross validation, this has gone to 20.65, more or less similar to your poly dot. Now similarly, I can go with tan H dot. So what I say is, probably you can very well try out all these models which are based on which you can very well assess. This is a hyperbolic tangent, hype-tan. So I am trying to fit a hyperbolic tangential model to this data, a support vector machine, which is the hyperbolic tangential support vector machine. Based on this, if I am looking at, yeah, this model is not doing a good job at all. Here again, the hyperparameter scale is set to 1, offset is set to 1, but I can very well play around with the different values of scale and offset to see if there is any kind of an improvisation in the model. So here the training error is coming out to 26.36%, which looks like a much higher error, whereas the cross validation is much more higher, 29.08. So probably in this case, the hyperbolic tangent kernel function may not work at all. Similarly, I can try out a Laplace dot. Right, probably I want you to try all of them. Right, I am using a Laplace dot kernel, fit Laplace. Again, for the fitment, I am using another different model. I am using a Laplace kernel here, which we don't have as a part of the SVM function in E1071 package, whereas Kernlab package is providing me that kind of an advantage. And if you are looking at fit Laplace, here the things are slightly better. Right, number of support vectors are 2400. This is the value of the sigma parameter. 19.52% is the training error, slightly higher than the RBF dot, but when it comes to the cross validation error, it's only 20.49, ending up to be the least possible in the overall set of functions. Similarly, I can look at the Bessel dot, wherein I am using the Bessel function. Bessel dot is something that I am using. So the kernel function that I am using is the Bessel function here. Okay, again the default parameters. Now you see so many options that are there in front of us, where we can change the different parameters. Here also sigma, order and degree are the three parameters that are set as 1 by default, resulting in a training error of 21.62%. So all of them are differing in the overall process. Cross validation error is 23.08%. So always you should believe in the cross validation error compared to the other ones, because this is the one which is executing it with different sets of combinations of values, and based on that the accuracy is typically being computed. Similarly, I can go with ANOVA dot. Let me quickly finish up the process. Now each of them I have the option. Remember always, in each of the kernels that I have said, I have the option to change the default parameters, play around. I can again loop in with respect to each of the default parameters, and again within each of the default parameters I can execute this entire set of processes and see what is happening to the training errors as well as the classification errors. So that way the whole process keeps repeating, which could very well be used for our overall understanding of the model. So the ANOVA dot is being used, which is consuming a good amount of time out here. Let's see how the ANOVA dot is performing on the training error. So we could see for each of the mechanisms what are the training error, what are the cross validation error, especially when you have done a cross validation, that would be more helpful. In this case, looks like ANOVA is a thrashable model altogether for this data, which you could see that the training error is approximately 79.99%, almost 80% is the training error out here, and cross validation error is to the extent of 45.47%, still much higher. None of the cross validation errors are in 30s, but this one is more in 40s as well. Now I have two more things to just see. So even if I don't know mathematically what each of these functions typically mean, but because of the presence of tools, we can very well execute all the different types of kernels, because at the end of the day what is more important for me is the success with respect to the classification of the data, the minimal error rate when it comes to the classification of the data, which can quite comfortably be accomplished. So here it looks like the support is out of bounds, so probably I cannot use the spline kernel in this mechanism, right? A few important elements are going out of bounds, so I cannot use the spline kernel here. So let me see if I can go ahead using the string kernel. So we need to see why we can't use the spline, but yeah, whatever are the ones that we have used, we could see that these are the different. Again here also we could see that one of these different kinds of kernels is what that you have to specify. So probably these two we are omitting for the time being. For all these different kinds of kernels, we got a classification error, which is from the training data, a misclassification error, one from the training data, and two from the cross validation, because we have set the cross validation parameter to be 10. So the process is executed in such a way that different combinations are taken as training data, the testing is performed, and the misclassification rate is computed in each of the scenarios and is given as a result for us. And now in each of the cases the parameters that are being used are different. Sigma is the parameter in one case, right? We'll have different parameters associated with the scale parameters, the order parameter, the sigma, the degree. So for different kinds of parameters we are having, for different kinds of kernels we are having different sets of parameters. So we can very well play around with the parameters, choosing different values of each of the parameters based on the kernel function that we have chosen. Now, assuming that the default ones are the most optimal out of all, now we can get into the process of prediction. So let me use the pred linear. Pred linear is something where I am trying to predict. Now I am using the testing data, right? I'll use fit linear, the model. I am predicting the fit linear model with my test data. Right? So that is what I am calling as spread linear. Similarly, I'll use fit poly, and I am calling that as spread poly. And similarly, I am using fit radial or fit RBF. No, what did I call that? Fit radial. And this is called as spread radial. Then we are talking about fit hype tan, fit Laplace hype tan, fit hype tan, and we are talking about spread hype tan. We want to see on the test data which one is doing a good job. Similarly, I want to use fit Laplace, and I want to store it in spread Laplace. And similarly, we can very well use fit Bessel, and I want to use it, I want to name that fitted value as spread Bessel. These are all based on the default parameters itself. Remember, we can have the option of changing the parameters, creating n number of new models and testing them out. So that is the kind of a complexity. So I can very well use fit ANOVA, and this I can call it spread ANOVA. So you see, with one single function, how many models can be created from the and can be used for the comparison purposes. So we have 7 different kinds of models created, predictions being done. So I'll create a table, one containing the actual data, which is test data dollar health status. That's the actuals. And along with that, I am also taking the predicted values. So first let me take the spread linear. So the first one is telling me the accuracy is coming across the diagonal. So 1322 are the total number of observations. 1014 plus 25. 1039 is the accuracy out of 1322. So resulting in 78.59 being the accuracy. So if I am looking at the error rate, it is 21.41%. For the vanilla dot, on the testing data, the error is 21.41%. Now let me go ahead with spread poly to see if there is some kind of an improvement. The spread poly is going very pathetic, right? It has simply predicted that all are average, whereas the reality is some of them are excellent and some of them are poor. So those ones are misclassified. So the overall accuracy of the model is much higher, but it did not do a good job because all others are being classified as much poorer in a poly dot kind of kernel. So the overall accuracy is much better. It's only 19.52%. I mean the error rate. The overall error rate is only 19.52%, but it came out because everything is being classified as average, and average you have big number of values coming under the average. But if you are going with a radial dot, more or less similar, 1068 is the correctness. 1068 divided by 1322, 80.78, and the accuracy coming out as the error rate coming out as 19.22%. Even here, because everything is being classified as average, things have come out much better. Similarly, spread, I am using hype tan. In this case, 33 plus 939, 972 looks like the accuracy of the model, wherein 73.52 working out to 26.48 is the error that is associated with the model out here. going with Laplacian again. So what I suggest is you should actually change the parameters and based on that keep redoing the model. So it's also Laplacian is also going with 1068 being the accuracy, which is more or less similar to that of your radial, resulting in 19.22% even with Laplacian kernel as well. But what we could see is majority of them are being predicted as average itself. Only 8 of them are being predicted as poor. Similarly, going with Bessel, Bessel also has done a decent job. 1049 is the overall accuracy out of 1322, resulting in 20.66% being the error. But even in this case, I could see that majority of them are being put under the category of average itself. And finally, I could also look at the ANOVA predictor. ANOVA predictor has put majority of them under the poor category. That is the reason I could see that the accuracy is only to the extent of 278 out of 1322. The accuracy is 21, which means almost 78.98% is associated with the error. So that is how we have looked at the error rates with each of the models, and I could clearly see that probably I could have gone with polydot or RBF dot, and now what I can think of is going with a polydot or RBF dot or Laplacian dot. I should change the different values of the parameters and see if there is any kind of an improvisation in the model that is occurring, so that the overall classification accuracy is improving and the overall error rate is falling. Now, once we have done that, this Western Watkins multi-class SVM, exactly similar to what we have done as a part of bounded constraint SVM. The only difference, as I have shown in the KSVM function, the only difference that you bring out is instead of using type equal to C hyphen B SVC, you will use it as KBB hyphen SVC. That is what is the Watson-Watkins native multi-class. So just for a quickness, I want to test this with respect to these three: radial, polydot and Laplace dot. Right? All else I will keep them to be the same. Right? So that we can very well see if there is any kind of an improvisation in the model because of changing the model, changing the type to any one of them. So let me call this fit poly. Let me take it. Everything remains the same. Only the type, instead of CSVC, I will be changing the type to KBB-SVC. That's the only difference I will bring in. Name wise, let me change it. Fit poly, or probably let me put it here, fit Western Watkins poly. So let it execute the fit Western Watkins poly. So similarly, I will execute the radial dot as well. All else remaining the same. The whole process is the same. So that's where instead of poly, I'll call it as radial dot. Oh, RBF dot. Sorry, not the radial dot. I'll take it as RBF dot. and I can also look at Laplace dot to see only three of them I am looking at right now, but you can very well try in the real world. You cannot, I mean, this is how you will change different sets of models with different values of the inputs to finally come out with the best accuracy and the error classification for any kind of data set. So here I am looking at only these three because these are the three ones that have resulted in the top three when it comes to the training errors, classification errors, cross-validation errors, or even when I have tested it out on the test data. So I want to see which one is coming out better. So when I see fit WW poly, still I could see that the training error is 19.97% here, right? The same one. Now when I'm going ahead here, the error rate is 19.97 with the training error slightly reduced. And when it comes to cross validation, yes, it came down to 20.16% with respect to the polynomial kernel. Similarly, when I am going with radial kernel, let me see what has come out. When I go with radial kernel, fair enough. So I will go with radial kernel. So it is coming out to 18.38%, right? This RBF dot is giving me on the training error, it is 18. Again with the same set of parameters. Now parameters can very well be changed. Let me reiterate it again and again. So here the training error is 18.38% and here it is still 20.65%. But similarly when I am executing the Laplace kernel, here 19.48%, and when it comes to the cross validation error it is 20.36%. so these are the percentages. So looks like polydot is much more appropriate, but let me go with pred ww poly. Pred ww poly, we are using the predict. The function that we are using is fit ww poly, and along with that we are using the test data. Similarly, pred ww radial, fit ww radial is the model that we are using, and pred ww radial is our predicted value. And similarly I can go ahead with the Laplace as well. So that's how you have so many options that are there in front of you. You may have to try all the possible combinations and before you make available a particular model for the prediction purpose, right? So now once our predicted values are there, you can very well take the tabulation wherein you are taking test data $health underscore status, which I am taking it as the actual values, and the predicted values you can very well take them from predict ww poly to get the accuracy 1066 in this case. Again 1066 out of 1322, resulting in 19.37% being the error on the testing data when I am going with. And similarly when I am going with the radial out here, 1068 it's continuing, right? The radial, the solution is continuing more or less. So 80.78 resulting in 19.22%. Even when I am going with Western Watkins multiclass SVM, And finally, when I got into the Laplace, this is also 1068 giving me similar kind of result, right? So even in this case things did not change, the same 19.22%. So again we could see that one of these three itself, unless I really change the parameters to some extent, if I'm using the default parameters, I'm not able to improvise the model. I'm not able to reduce the misclassification error beyond any of the percentages. And the same logic goes with third in the same category, wherein I can very well use SPOC SVC as the type for Kramer-Singer native multiclass. Again, everything remains the same, right? I can very well use Kramer-Singer. So I should be using it as SPOC hyphen SVC. So let me again go back to our fittings, right? Let me take all these three again. Fit, instead of WW poly, I'll call it as CS poly. All else remaining the same, I'll call it as, which is Kramer Singer. So I'll call it CS poly. All else remaining the same, instead of KBB SVC, we are calling it as SPOC SVC, right? So this is a polynomial kernel that is fitted, wherein the type is Kramer-Singer multiclass support vector machine. So I can repeat the same process for the others as well. Again, let me look at only the radial kernel. So I will be using RBF dot here, and I would call this as fit CS radial. So let me try with these two itself rather than going ahead again with Laplace. Now you know how to do with all the different possible combination. Alright, now let me just check what is the output of each of these two models. Oh, this model with a polynomial dot, especially with parameters degree equal to 1, scale equal to 1, offset equal to 1, cost equal to 1, which are set as default parameters, looks like the training error is only 20.71%, but it is looking very dangerous when it came to cross validation error, making it 43.51%, which means this model may not be used as it is with the default parameters. And what about the radial RBF dot function? This is still okay. The training error is 17.63%, and even the cross validation is around 20.33 with the default. Now once I know this, I can very well go with Pred CS poly. So the Pred CS poly again is going with the predict function, where I'll be using fit CS poly as the model, and I'm using my test data. So based on that, I can very well create a table where I'm using test data $health underscore status, which is the actual values, and Pred CS poly being the predicted values. Using this, the table is saying only 1064 is the accuracy. All of them are being predicted as average itself. Whereas now I can think of using spread CS radial to see if there is some level of improvement, and here also I'll use the model fit CS radial. And a tabulation, in this case the tabulation is giving me 1057 plus 14, 1071 is the accuracy, which is probably the best that we have got till now. 1071 out of 1322, 81, resulting in a error rate of just around 18.99% going with this radial. So if I have to try out, it's better that I try out all the other all different parameters for each of the different functions, so that my final objective is to create n number of models which will result in reduction of my training error, cross validation error, and along with when I'm applying this model on my test data, it should definitely improvise the accuracy of the model, means the misclassification error rate should come down quite drastically. So that is how I have to get into the understanding of these models. So in short, if I have to talk about the support vector based classification, right, I can rely on two major packages. Either I can rely on E1071 package, where I can very well use the SVM as a function, wherein this can help me in executing the CSVM algorithm as well as Nu-SVM algorithm. Or I can rely on Kernlab package, where we have a function called KSVM, which can execute all these 5 types of classification model. So we need to be comfortable with respect to these two models, because within them they give us the options to really change one, the cost, the new, and various other parameters which are general to almost all the models. Then the kernel is something that I can very well change. So this SVM supports 4 different kernels, whereas Kernlab supports 8 different kernels. So I can very well change the kernels and play around. And kernel specific parameters, kpar, I can very well change all the kernel specific parameters in these models. So that's one more flexibility that I am getting. And the type is all these, any one of these 5 I can specify. So many options are there within the model with the same function, either SVM or KSVM. So this is where a good amount of understanding and the expertise in terms of the usage of the model, the usage of support vector machines for classification purpose is very much anticipated. I hope this session should give you some basic amount of introductory understanding in terms of using the support vector machines for the classification purpose, and what all modifications you can do to the formulas and functions in R, so that different kinds of models can be implemented and the different results can be observed more meticulously. This is where I come to the end of this session regarding the support vector classification. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.